Good morning. Welcome to our first online class. Today we will be relating the graph of volume against temperature to the establishment of the Kelvin scale and ultimately absolute zero. But first, let's review a couple of things. One, let's remember that when things are heated, they expand, and when they are cooled, they contract. Secondly, according to the kinetic theory of heat energy is the movement and vibration of atoms. So let's talk about Lord Kelvin, who did an experiment where he changed the temperature of a fixed mass of gas and measured the corresponding volumes. He plotted a graph and noticed that it was a linear relationship, that is, a straight line graph was obtained. From this, he could predict volumes of gas within the range of his experiment, which is known as interpolation. A more formal definition of interpolation is when you get values within your graph that are within the range of the experiment. So if let's say, for example, this particular experiment was only done from about minus 10 degrees Celsius to about 100 degrees Celsius, when you can make predictions about the volume of the gas within that range of temperature, that is known as interpolation. So let's say, for example, if you wanted to know what the volume of the gas would be when the temperature was 50 degrees Celsius, you would start and you would mark a vertical line from 50 degrees on the temperature axis, which is your horizontal axis, all the way up till you meet your line of best fit, and then you make a horizontal line over to the vertical axis and you read off that corresponding value. So for example, if let's say the temperature was 50 degrees Celsius, it would correspond to a volume of 2.5 cubic meters. So even though it was not one of the points that were plotted, one of the actual values read from the experiment, you could make that prediction with some great degree of accuracy. On the other hand, if you wanted to make predictions outside the range of your experiment, you would have to extend your line of best fit, and this is known as extrapolation. When you extend your line of best fit, you don't normally extend it with a solid line. You would extend it using a dotted line to illustrate that it is not within the range of the actual experiment that was conducted. So Lord Kelvin extended his line of best fit to the horizontal axis, where he logically surmised that the volume of the gas would be zero. He thought that this would be the coolest temperature possible because the volume of the gas could not become anything less than zero. In other words, it could not be negative. So when Lord Kelvin extrapolated his data, he found that the coolest temperature possible would be about minus 273 degrees Celsius. And he called this absolute zero. He called it absolute zero because it was absolutely the coolest anything could be in the universe. It was not a virtual zero like on the Celsius scale where you could get below 0 degrees Celsius. This was absolute zero because you could not get below 0 Kelvin on his newly invented scale. Technically, absolute zero does not really correspond to minus 273 degrees Celsius. Specifically, it is about minus 273.15 degrees Celsius and negative 459.4 degrees on the Fahrenheit scale, which is not much in use, only in Belize, the United States, and a few other Caribbean countries. The two main scales that are in use today in science the world over are the Kelvin scale and the Celsius scale. So in theory, absolute zero is possible. However, in reality, it is impossible for three reasons. The first of which is, inevitably, when gases are cooled down, they contract, yes, but they don't contract and contract forever and ever. There is a limit to their contraction. When gases are cooled, they must first change into a liquid. Difference between gases and liquids is that gases can be squashed. Their volume can decrease. But when it comes to liquids, they cannot be squashed. Their volume is fixed. And the more you cool down the liquid, then it will change into a solid, which also cannot be squashed. So in theory, the volume could become zero, but in reality, the volume will never become zero. And as such, you cannot reach absolute zero, minus 273 degrees Celsius. Another reason is that heat is radiated everywhere throughout the universe, from all the different stars and all the different galaxies. So even when you think you are in empty space and it is very cold, you don't actually reach a temperature of 0 degrees Celsius. The average temperature of empty space is about 3 Kelvin, technically 2.7 Kelvin. We say rounded off to 3 Kelvin. And in empty space, you don't ever reach anything that is close to absolute zero. You're always 1 or 2 kelvins above, because heat will always reach you in what we call the microwave cosmic background radiation. And the third reason comes to us from quantum physics. If you've ever seen the movie Avengers Endgame, you've heard the word quantum many times. One of the principles of quantum physics is Heisenberg's uncertainty principle. It says that whenever you're looking at a particle, you can either know its position or you can know its velocity, in other words, its momentum, but you can't know both of them with the highest degree of accuracy at the same time. So you can know where it is, but you don't know how fast it's moving, or you can know how fast it's moving, but not exactly where it is. So, how does this apply to not reaching absolute zero? Well, if a particle reached absolute zero, it would no longer be moving. Remember that heat energy is the kinetic movement and vibration of atoms. So if it is at absolute zero, it would have no heat energy, no movement at all. But if something is not moving, then you would know exactly its position and you would know exactly its velocity, but that would violate the uncertainty principle of quantum mechanics, which has been proven to be true. So let's review what we learned today. Lord Kelvin did experiments with gases that were fixed amounts of gases, and he changed the temperature to see how their volume would correspond. He noticed that as you heated up a gas, its volume expanded, and as you cool it off, its volume decreased. And so he said, well, how far can its volume decrease? It can go anywhere below zero. The most it can be is zero. The lowest it can be is zero. And so he extrapolated his data and he found that that would correspond to a temperature of minus 273 degrees Celsius. So that is how the volume of a gas related to its temperature led to the Kelvin scale and ultimately absolute zero.